Now we'll see other variations of this 2PL. We have two other variations. One is strict 2PL, second one rigorous 2PL. So we'll study one by one. To understand them, first you should understand strict schedule. So what is strict schedule is, you have, let's say, some set of transactions T1, T2, T3, and if T1 updates a database item A, let's say T1 is updating some database item A after reading, but reading is not compulsory. So this is compulsory. Let's say if T1 updates a database item A, then after that if T2 reads or writes. So if T2 or any other transaction has conflicting operation like read of A, otherwise write of A, whatever it is. So before these operations, this transaction T1 has to commit this variable. That means, so this T1's commit should be before T2's read, otherwise T3's write. That is called strict schedule. Not only variable A, every variable should satisfy this condition. That means if T2 updates a database item A, now see here, again T2 is doing the same thing, then T2 should be committed before T3 again writes it. So that's why T2's commit should precede T3's any updations or readings. So here again T3 is writing it, correct? So this T3 has to be committed, this T3, before others again read or write. That's it. So such schedule is called strict schedule. I will give you one schedule, you tell me whether it is strict schedule or not. See this one, T1, T2, T3, T4. So read of A, then write of A, then here let's say write of A and write of A. So here commit, then here it is commit, then here it is commit, and here it is commit. So is it serial schedule or not? We will see. Every updation we should focus. So here there is one updation by T2, correct? Now any others are updating or reading that A? Yes. Here after T2, T3 is updating it, then definitely this updation should take place after commit of T2. So yes, you are right. So commit should be preceded before this T3's operation. Similarly, here one more updation is going on, then it should be committed before others do some activity on A, read or write. So yes, so here this write of A, if you see, so before that this T3 is committed. So now this is legal. So finally it is strict schedule. To understand strict schedule clearly, focus on every updation. See, mark it. So this updation should be, whoever updated this one, T2, right? So T2 should be committed before others read or update that A. That's it. So that's why you are right. So here commit is taking place first. Similarly here there is one more updation. So this transaction T3 which is updating A, that should be committed before others write it. Here T4 is writing it, right? So before that this writing should be committed. That means this transaction should be committed. It's so easy to understand. Now we will see strict 2PL. What is strict 2PL is? It is a 2PL. You know what is 2PL, right? Two-phase locking, like conservative 2PL and basic 2PL. That means there are two phases again. Locking phase, unlocking phase. Once you unlock any data item, then further we cannot lock it. Correct? Not only that variable, any variable you cannot lock. So every transaction has to satisfy that condition. Let's summarize it. Every transaction can lock any number of data items, but once they unlock any data item, further they cannot unlock, further they cannot lock any other data item. So that is what 2PL protocol. Now strict 2PL is also one of such protocol, but what is that strictness? I will tell you. So in strict 2PL, whenever you have exclusive lock on some database item A, which is made by some transaction Ti, let's say T1 is putting exclusive lock on A to write some database item, let's say, then such lock should not be released until this T1 is committed. After commit only we should release it. That means this should be the syntax of, that exclusive lock. So here see, exclusive lock is applied here, and after that this is commit point. After that only that unlocking should be done, unlock of A. Not only this variable A, every variable should, every variable whenever it is locked, same thing should take place. Example, there is another transaction T2. At this point, let's say suddenly that T2 has acquired exclusive lock on A. Then after that it should not be released. Then when it should be released, if you see, there will be a commit of this T2 after commit only this exclusive lock should be released using unlock. We know that, right? Unlock of A. This concept is called strict 2PL. Now it is easy to understand that what are you doing is, so this exclusive lock whenever you keep, most probably we use exclusive lock for write operations, correct? That means you are writing, so you are writing something almost, right? So that write operations whenever you do, then others cannot do the same thing. So others cannot do reading or writing on same database item A because you have lock. Sir, but we release it, right? Yes, when once that variable is released, you can read or write. But when are we releasing? We are releasing only after commit. That means finally, once a database variable is written, then others cannot read or others cannot write until the transaction which wrote first gets committed. So is it not strict definition? Yes, that's why strict 2PL allows only strict schedules, like only strict schedules. Whenever a schedule is not strict, it cannot be allowed, correct? So remember this point. Strict 2PL allows only strict schedules. Remember it. Now we'll see another variation, that is rigorous 2PL. So what is rigorous 2PL is, in rigorous 2PL, not only write lock, that means not only exclusive lock, even read lock also completely blocked. That means read and exclusive, every read and exclusive lock will be released only after commit of the transaction. We will see that. So every transaction, let me write the statement, every transaction Ti releases all the locks, not only exclusive, read and write, releases all the locks after commit statement, I can say. Example we will see. Consider this transaction T1, T2, T3, T4 and see this one, read of A, write of B, something, let's say read of A and write of B. And is it allowed under rigorous 2PL? We will see. If it is allowed under rigorous 2PL, then we should remember this point. We should always follow this condition. Every transaction releases all the locks after commit statement. So what we do is we put random commit statements because that depends on transaction. Let me take one example here. Commit is here and let's say committing is here. Let me commit here. Okay. So let me commit T3 here. Let me write commit of W3 here. We will see whether such kind of schedule is allowed under rigorous 2PL or not. Let's try that. For that, first of all, we acquire shared lock of A, but when it will be released after commit, then you will be unlocking A only here, right? Since this committing point is before this write of A, then this unlock, once this is unlocking is done, right? So this write of A, let me write little bit downside. So now since your lock is free, then T2 can acquire exclusive lock on A, correct? But when it can release it, this lock can be released only at earliest point is after commit. So here it will be unlock of A. So but before that, here itself you need that operation, correct? So what I want to say is this operation will be little bit moved, correct? So that's why I can say that only after commit of this T2 your read operation can take place. Then your question is, if this read is in between write of A and commit, will it be executed? No. So that's why I can say that as it is, this schedule is not allowed under rigorous 2PL. The reason is what? You have a read operation between write of A and commit of one transaction. But whenever we get write of A, to do that write of A, we acquire exclusive lock, but we don't release it immediately. But in general 2PL, we might release that immediately and probably this T3 can acquire it. But here the problem is every lock will be released at the end. So here if it is acquired, then it will be released here. Then your transactions read of A is placed here in between. So this exact schedule will not work. So for that, the alternative is, that means what your DBMS will do is, so automatically your T3 will be blocked, and when it will be released, here. This is a point where you are unlocking it, then T3 will be released, T3 will be released, correct, here. Okay, so whether it is read of A or write of A doesn't matter, but T3 will be continued from here. Similarly, what about this one, write of B? So write of B, so far nobody is acquiring that lock, but so here T4 can acquire exclusive lock on B, then he is going to release here unlock of B. There will not be any problem. Now only T3 is facing the problem. T3 got blocked and it will be released after this unlocking point of T2, which is at end of the commit. So what I want to say is the schedule which I have given to you is not exactly allowed under rigorous 2PL. It is allowed under basic 2PL. Why it is allowed under basic 2PL we will see now. Consider same set of transactions T1, T2, T3, T4. Let's take S of A, read of A, and we have, let's say, write of A, then let's say we have read of A and something write of B. Let's take this transaction. So their commit points are, let me fix here, let's say read of A, this commit is here and write of A's commit is here and T3's commit is, let's say, here, just for write of B's commit is here. Now question number 1, is it allowed under rigorous 2PL? Let's do again. So I have changed a little bit, I think. So we will see. So recall the strict 2PL definition. In strict 2PL, every write operation or every exclusive lock should be released at the end of the commit. Just remember it. So somehow we try to execute it as it is. So since it is read operation, so we will have shared lock and we can release anywhere. Let me immediately release it, right? So that is the difference between I can say rigorous 2PL and strict 2PL. In strict 2PL, immediately at any time we can release, but in rigorous we have to release this even shared lock also after commit. That's the difference. Now because of that, happily T2 can complete its write of A because we can have here exclusive lock on A, but the problem is that exclusive lock should be released after what? This commit. So this is the earliest point where we can release A. Then what about this one? This should be moved because if T3 tries to attempt this operation, then on behalf of T3, your DBMS is going to write shared lock on A. That will be cancelled by your DBMS and your T3 will be blocked and it will be released probably here. So finally what I want to say is this schedule is not allowed under strict 2PL after moving this read of A. So in the execution process, while executing the schedule, this instruction will be moved by your DBMS by a method called blocking, correct? So this is the way we can easily check whether given schedule is allowed under strict 2PL or not, rigorous 2PL or not. In the exam, if they give that kind of questions, somehow see, try to keep shared locks and exclusive locks and try to release them according to the rules of the strict 2PL and rigorous 2PL and try to execute the schedule as it is. If you can do it, then it is allowed under whatever the so-called algorithm. Otherwise, we say it is not allowed. Understand? So let's summarize it. What is strict 2PL and rigorous 2PL? In rigorous 2PL, every lock will be released at the end. But in strict 2PL, only exclusive locks are released at the end. Understand? Now, since you are releasing exclusive locks at the end, that means what? Only if you modify any data, then without committing it you can't release it, then others cannot hold it. Because of that, so automatically dirty reads will be first of all eliminated. We will see there will not be any dirty read in rigorous 2PL and strict 2PL. I will show that with simple schedule. Now see the schedule T1 and T2. Let's say T1 is doing updation of A, write of A. So T2 is immediately reading so that it is dirty read, correct? After that, let's say T1 is committing whatever it is. Then later, let's say T2 commits. Now definitely this schedule, if you see, it has a dirty read, correct? So whenever there is a dirty read, then you know the problems. So maybe your schedule may be recoverable, may not be recoverable, and maybe cascading rollback or may not be, right? So we will see that whenever there is a dirty read, definitely there is a cascading rollback. That's a problem, we know that, correct? So here, especially if power goes off here, then uncommitted, here power goes off, then still you have not committed T2 also, there is no problem. So this schedule is recoverable, right? See the order T1 to T2 order, and here also commit order is same. So it is recoverable but cascading rollback. If power goes off here, then we have to roll back T2, correct? So such schedule, whether it is allowed under strict 2PL or not, we will see. In strict 2PL, what are you going to do? Since T1's write operation appears first, then T1 gets, let's say, exclusive lock on A. Yeah, it is possible. So after that, what we do, when will we release it? So we will release it after commit, correct? So you are unlocking here. When you do that, then read of A never gets chance to read the dirty data. Then what I want to say is your T2 will be blocked and it will be moved to this point, correct? So I can say that, so your read of A can be done only at here but not here. So the schedule which we wrote, that cannot be as it is accepted under strict 2PL. So rigorous 2PL is stricter than strict 2PL, isn't it? So that's why this schedule is not allowed under rigorous 2PL and strict 2PL. So in that way, easily we can understand that your schedules, whenever you have strict 2PL, I understand one important point. In strict 2PL and rigorous 2PL, so which problem cannot arise? Automatically they allow only recoverable schedules. That is one important property. And moreover, strict 2PL allows only, see, cascadeless schedules, correct? Cascadeless. We have seen it. Because whenever you are updating it, whenever you are updating the data, so we are not releasing the lock until you commit, then only committed databases, otherwise committed values only can be read. So how can you get dirty data? There is no dirty data. That is what very important point in strict 2PL. In strict 2PL, no one can read dirty data. Just now we proved. So when there is no dirty data, no cascading rollback, no non-recoverability. That's why I can say that always. So strict 2PL allows recoverable and cascadeless schedules. So now since rigorous is stricter than strict 2PL, then rigorous 2PL also allows recoverable and cascadeless. Understand? So this is the idea about strict 2PL and rigorous 2PL. Now we will see why, whether recoverability and cascadelessness are ensured by other algorithms or not. What are the, one is basic 2PL, second one conservative 2PL. Let's try to understand that. Let's take same schedule T1, T2 and let's say write of A and read of A. There is a dirty read. This is the simplest problem which explains you dirty read, correct? Now it is allowed under basic 2PL. Why? In basic 2PL there is no such thing like we have to release the lock after commit or whatever. So simply I can lock here and I can unlock here, correct? No one can stop me because this is basic 2PL technique. So after unlock I am not releasing, I am not acquiring any lock. So I am using basic 2PL. Here simply let me put shade lock and let me release it. So I am following basic 2PL and I am allowing this schedule. But what if there is a commit here and what if there is a commit here? See the danger. If power goes off here, then committed transaction should be rolled back. So this schedule is non-recoverable, but still it is allowed under dash basic 2PL. Similarly, you check it out. Even conservative 2PL also is not caring about commit transactions or non-committed transactions, correct? So that's why even conservative 2PL also will have same problem. It allows non-recoverable schedules. When a schedule is non-recoverable, definitely it is not cascadeless also, right? So I can say that basic 2PL, let's write it, basic 2PL and conservative 2PL. Both are having same idea, right? With this model. So basic 2PL allows non-recoverable schedules also. The question, basic 2PL allows only recoverable schedules is a question. Only recoverable schedules? No. Conservative 2PL only allows recoverable schedules? No. Now similarly we'll see cascadelessness. Okay. So here I write cascadelessness. So first of all we write cascading rollback. Only cascading rollback. So basic 2PL allows only cascading rollback? Absolutely false, because even it allows non-recoverable schedule. That's why it is wrong. That's why it is wrong. Now we'll see cascadeless schedules. So basic 2PL allows only cascadeless schedules? No. It allows non-cascadeless also. Conservative 2PL allows only cascadeless? No. Finally this basic 2PL and conservative 2PL. So cannot guarantee recoverability, cannot guarantee cascade rollbackness, cannot guarantee cascadelessness. Understand? But strict 2PL definitely can guarantee cascadeless, correct? But we know one thing, whenever a schedule is cascadeless, then definitely that schedule is recoverable also. Now if you ask this question to strict 2PL, Mr. Strict 2PL, you allow only recoverable schedules, isn't it? Obviously, because moreover it allows only cascadeless schedule, that's why it is right. Now Mr. Rigorous 2PL, what about you? See, strict 2PL allows only recoverable, I also allow only recoverable schedules. So in that way, easily we can answer any question, theoretical question related to these concepts. Understand the concept clearly, then remaining things, see, you know what is recoverability, what is cascadelessness, what is cascading rollback. So why should I teach all these things like, results? Why don't you try on your own, correct? That's a good idea. So that's why whatever the things which I have not taught you, then you just think about them, understand? And if you don't understand, please ask me. So through social networking or anything, I can answer. Right. Now we'll see the relationship between rigorous 2PL, strict 2PL and basic 2PL and conflict serializability. So we know that rigorous is a strict condition than strict 2PL. That's why a schedule is allowed under rigorous, then automatically that is allowed under strict 2PL, correct? So we know that. Similarly, a schedule which is allowed under strict, automatically that is allowed under basic 2PL, but not vice versa. That means if a schedule is allowed under basic 2PL, in that, so write lock may not be released after commit statement, right? It is not compulsory. That's why there are some schedules may be allowed under basic 2PL, but they might not be allowed under strict 2PL. Similarly, strict to rigorous we can understand. So this is quite easy to understand. But what is the relationship between conflict and basic? We will see that. We know that basic 2PL allows only conflict serializable schedules. That means if a schedule belongs to basic, let's say S belongs to basic, then definitely S belongs to conflict serializability. So that means definitely I can say that basic serializable, basic 2PL schedules are subset are equal to conflict serializable schedules, correct? Because an element belongs to basic set, then automatically that is belongs to conflict serializable set. But are they equal? Otherwise, a basic is proper subset of conflict serializability. We have to check. That means, is there any schedule which is actually conflict serializable but not allowed under basic 2PL is the question we should answer. Otherwise, the second thing we know, is there any schedule which is allowed under basic 2PL but not conflict serializable? Such schedule does not exist because basic 2PL allows only conflict serializable schedules. But the question, is this allows all the schedules, all the conflict serializable schedules is a question. For that answer is no. That's why the relation is like this. Conflict serializable schedules are superset or equal to basic 2PL. They are not equal, but strictly superset of basic 2PL. So we'll see the reason. This is the schedule. This cannot be allowed under conflict serializability. Sorry, basic 2PL, but it is allowed under conflict serializability. We will see. So here there is this one conflict here, second one conflict here. So there is no cycle. You can check it out, right? So this is conflict serializable schedule, but not allowed under basic 2PL. Okay, so this is conflict serializable but not allowed under basic 2PL. We will see why. So to allow this under basic 2PL, we should achieve locks, right, using the 2PL conditions. So we know the 2PL conditions. Once unlocking is done, no more locking. So here slowly we understand it. See, T3 wants exclusive lock on X, correct? So this is the point which is the, I can say latest point where this T3 can take exclusive lock, correct? So even you can give exclusive lock here, unnecessary. So better you give here so that concurrency will be allowed. Now immediately you unlock, correct? So that is the best possibility. We are trying best possible way to achieve 2PL. So, but before that we have read of X. That means, so here really T3 wants exclusive lock on X. We should release this shade lock. T2 is going to have shade lock here. Then we have to immediately release it, correct? So again, this is the best possible way we can release the lock. Now the question is, what about this right of Y? When are you going to release it? Definitely here. This is the best one, right? Even you can release here, but unnecessarily you are reducing the concurrency. So let me unlock here. But when are you going to lock it? Here, anywhere you can lock. but if you lock here unnecessarily, others cannot hold it, right? That's why don't lock unnecessarily. Whenever it is necessary, you lock it. So the necessary point to lock y is this one, right? Exclusive lock on y. Now see, in this part, definitely we need a lock. No one can ask that lock at that time, correct? Now come to y. Even T2 wants lock on y, correct? What is the earliest point? What is the best point we can take the lock here, right? But the problem, if you take lock here, that is the best possibility. But already before that we unlocked here. If you don't unlock, we cannot give lock to T3. If you don't give lock to T3, this schedule is not allowed, correct? That's why we have to do unlock of X here. Then how to handle this one? The only possibility, if you really want to achieve, if you really want to do perform read of y, so definitely we have to lock it. When? Before unlocking. So what we do is here before unlocking here, this is the point where you can go for shade lock on y, correct? But if you have shade lock here on y, see here, T1 is having exclusive lock here. That means you are already holding a lock on y. How he can take? For that you have to release it, but if you release it, then you can't access the read of y here, correct? So definitely we have to hold a lock from here to here. Sir, I do one thing, I take it, then I release it, then again I take it. You can't take here because after unlocking, no locking. That's why here in this area you can't lock. So that's why whatever the way you try, this is the idea. So you go through this idea and try to, it is just reasoning, that's it. So in that way you reason it and you will realize that whatever the way you try here, you can't allow it under basic 2PL. Maybe, by blocking and by moving the instructions we can allow, but I'm not talking about that. I'm talking about exact schedule. This is not allowed under basic 2PL, but it is conflict serializable. That's why, so basic 2PL schedules are only conflict, of course they are conflict serializable, but only few conflict serializable, not every conflict serializable schedule is allowed under basic 2PL. That's why this is the relation between these two, and this is the counter example. This is the example to say that conflict serializability is superset of basic 2PL schedules. So this is the story about this basic 2PL algorithms and conflict serializability. Now the problem with basic 2PL is what? It has deadlock problem, right? To avoid it, we have to use deadlock prevention algorithms, but deadlock prevention algorithms are going to cancel your transaction so many times. Do you allow it? Because of that, unnecessarily, you will be going to inefficiency. That means when a transaction is cancelled so many times, then it is before cancellation, it is consuming a lot of computer resources, correct? And you are restarting again. That is the idea about deadlock prevention. What deadlock prevention algorithms are going to do is, example, you have a transaction. Somehow, whenever they detect that this system is going to deadlock, then simply they cancel some of the transactions. Then again they will restart them, however. Okay, but whenever you cancel it, before cancellation, it might use a lot of computer resources. Then it wasted a lot of time of computer and everything, right? So that's why most of the times people go for other models, like rather than these deadlock prevention algorithms, we should find out other alternatives. But at this moment you remember that yes, at least we can try this one. What is that? Basic 2PL plus deadlock prevention algorithms is one combination which can be used for concurrency. Now strict 2PL also we can use. Even strict 2PL has that same problem, deadlock. That's why even you can go with strict 2PL and this one deadlock prevention algorithm. In that way, so any 2PL algorithm you can take, rigorous also you can try, and you can go with deadlock prevention algorithm. We are going to see what is deadlock prevention algorithm. At this moment we have these various algorithms. And one more thing, we know that the advantage of strict 2PL and rigorous 2PL is they allow only recoverable schedules and recoverability. Please recall, so recoverable schedules are good and they are easy to implement. Second one, cascadeless schedules also, they don't waste computer resources. No unnecessary cancellations of transactions in cascadeless cascadeless schedules, correct? So that's why, so rigorous usually, so DBM, commercial databases implement strict 2PL, otherwise rigorous 2PL. And understand, the problem with basic 2PL is it has deadlock followed by one more thing. Of course everything has deadlock, but it is unnecessarily sometimes allows non-recoverable schedules, and sometimes it allows cascading rollback schedules. So what happens to recover your schedule? Sometimes, example, some mistake happens, we have to recover. We know the recovery theory. Please go through my recoverability concept. On that you learned that already. So to recover the schedules, we have to cancel the transactions. It's a waste of time. That's why people generally don't prefer basic 2PL. So they prefer rigorous, otherwise strict 2PL over basic 2PL. This is a story. Now conflict serializability, we know that, right? It is, we can't implement easily. That's why we are going for implementation models. They are nothing but basic 2PL, strict 2PL and rigorous 2PL. Now I'm going to teach you another kind of protocols. They are timestamp based protocols. So far we have seen locking protocols. So we have timestamp based protocols. Before going to timestamp based protocols, I would like to tell you one more important point. This is about lock upgradation and lock downgradation. If example, let's say you have, if so far we have not discussed lock upgradation downgradation, right? When you have a 2PL protocol, then how to understand the 2PL, whatever it is, with lock upgradation and downgradation. We know about this ordinary model where whenever you lock it, it is first phase. Whenever you unlock it, it is second phase, right? So in that way we can separate locking and unlocking. But what about lock upgradation and downgradation? How to deal them and how to, where to map them is the question, right? Remember. So with respect to lock upgradation, downgradation, 2PL is defined like this. Lock upgradation you can do only in first phase. That means growing phase. That means in locking phase. And downgradation is treated as unlocking, so that will be considered as unlocking. Once you do downgradation, you can't do further upgradation and you can't do further locking. Similarly, so you can upgrade in only in first phase. That means you can upgrade any number of times any database items. But once you downgrade any item, after that no further upgradations. Understand? So you know this model, right? So your 2PL protocol has two phases, right? This is growing phase, this is shrinking phase. So upgradations are only possible in this phase, upgradation. UG. Downgradation is only possible in shrinking phase. If you understand, if you remember that, then easily we can understand again this 2PL protocols, not a problem. Okay. So now we will go to the another model, that is timestamp based protocols. So first of all, I will teach you what is timestamp. Then after that we will see protocols related to that. Okay.